Yes. Okay. Wait a second. Okay. You see the slides? Yeah.
Yes.
Okay. So good morning. Good morning, at least for those who are in Europe. So my name is Alessandro Ciani, and I'm a postdoc at QTech TU Delft. And first of all, I'd like to thank the organizers for giving me the opportunity to give this talk here today, whose title is, the talk is about our recent work, that is hardware encoding grid states in a non-reciprocal superconducting circuit. And this work has been recently accepted for PRX, and it's joint work between myself, Martin Riemertz from RWTH Aachen, that is the first author of the paper, Stefano Bosco, currently at the University of Basel, and David Di Vincenzo as well from RWTH Aachen. And let's say the talk will be about, grid states. It is actually also fairly connected to what Jonathan was talking about. And it is about grid states, but maybe not in the standard way in which we think about grid states, in the sense that here we aim at finding a way to finding a system that has the GKP Hamiltonian, that is the sum of the stabilizers of the GKP code, made Hermitian, of course. That is the Hamiltonian, and so we want to engineer the grid states passively, so as eigenstates of this Hamiltonian. And our claim is that you can actually, in principle, do it with this ideal circuit that has this, let's say, non-standard element for circuit QED, but okay, it is a well-known element that is the gyrator. Okay, so what I'm going to talk about in this talk, which is mainly the content of the paper, is the following thing. That's to say that I think we nicely showed the connection between very different topics. That's to say GKP states. The Hofstadter butterfly, I don't know if everybody's familiar with what the Hofstadter butterfly is, but I hope you will understand, and you will understand the connection with GKP states from this talk, and also the that everything can be actually realized by, it's emulated by this circuit in a specific parameter regime. And the reason is that essentially this circuit emulates the mechanical problem of a charged particle in 2 dimensions, in a constant magnetic field and with a cosine potential, or cosine plus parabolic potential. What I'd like to take out of this talk is actually this nice connection between these quite different fields. Okay, so during the talk, I will always I will develop, let's say, the math using this language of the charged particle and magnetic field, mainly because it's the way I mostly understand it. I also think that it's, let's say, the easiest way to look at the problem, because you have this mechanical analogy in mind. And then I will show that, I will argue that the circuit we are considering actually emulates this system. So we consider a charged particle let's start with the case of a cosine potential. So you have a vector potential, of course, and the magnetic field is orthogonal to the plane. So when you see like a periodic potential, the first thing you think about is to try to apply Bloch's theorem. But then you soon realize that this is not possible, because the standard translations, the discrete translations, do not commute with the vector potential. And so there is no standard Bloch theorem. However, and this was understood like in the maybe 60s or 70s, there is a way around. And the way around requires you to introduce new variables. that are so-called dynamical momenta and guiding center variables. So pi 1 or 2, R1, 2, which are gauge invariant. And the introduction of these variables is actually physically motivated, physically motivated by the solution of the, let's say, what I would call the cyclotron motion, although we're just in 2 dimensions, when v equals 0. That's to say, okay, the dynamical momenta are simply m times the velocity, essentially, taken as operators in this case, while the guiding center variables represent the center of the cyclotron motion. So you have your magnetic field, your particle will start to spin around the center. Those are the guiding center variables. Interestingly, what happens if you do the quantum mechanics right, is that these 2 positions, although they are 2 positions, effectively, they do not commute. And they have the following commutation relation here. Once we do this change of variables, the Hamiltonian ends up in this form here. And at this point, you clearly have the idea of defining new translation operators that actually shift the guiding center variables, because the Hamiltonian is still periodic in the guiding center variables. And these are indeed the so-called magnetic translation operators. So magnetic translation operators that shift the guiding center variables. And indeed, it's quite easy to show that these operators commute with the Hamiltonian. However, you end up with another problem, that is that magnetic translations do not always commute with each other, but they only commute with each other when the flux in one unit cell is an integer times the flux quantum that here is h divided by e, so it's not the superconducting flux quantum, of course. And so let's say you can use this approach of the magnetic Bloch theorem if you have integer flux quantum in the unit cell. So now I will try to let you understand that in a sense this is already connected with GKP states, so with the GKP code. Because what do we do in order to to resort to a magnetic Bloch theorem? So suppose that we have the following situation, in which in one unit cell we have a flux quantum, so 1/2 flux quantum. So P over Q is 1/2 in this case. So the strategy is, of course, to make the unit cell bigger, so that in total you have 1 flux quantum in this simple example. So you would take a magnetic translation that translates R1 by 2 L0 and R2 by L0. An alternative is, of course, also to consider the opposite case. These are all valid choices, but the physics, of course, will not depend on this choice. But in a sense, if you think about it, this is exactly what you're doing when you construct the GKP code. So looking for translations that commute in phase space, because in this case also R1 and R2 are not commuting variables. So this already gives a bit the connection. Okay, so now in order to see manifestly that this gives rise to the GKP code in the guiding center variables, importantly, so the quantum information will be encoded in the guiding center variables. What we do is this lowest Landau level projection. That's to say, we solve this part of the Hamiltonian that can be trivially solved by introducing annihilation and creation operators. So we solve this Hamiltonian that has only the guiding center, the dynamical momenta as variables. And then at this point we so this gives rise to the so-called Landau levels. The spacing is given by the cyclotron frequency, so EB divided by M. So you need large magnetic field for the following, because we assume that this level spacing is much larger than this energy scale here, so that we can project everything onto the lowest Landau level, which is, of course, highly degenerate. So we end up with a Hamiltonian that has only the guiding center variables as variables. So this Hamiltonian looks like this. So it's the sum of two magnetic translations. Here there is a quite bad parameter rescaling, I have to say. So this creates some problems in the sense that here you have this exponential factor here. But at any rate, so once you do a trivial variable rescaling, so that you introduce variables so that the commutation relation is gives I, the Hamiltonian has this form. So now, since this is a GKP, I mean strongly GKP based conference, so you clearly see that for P over Q equal 1/2, you actually end up with what we call the ideal GKP Hamiltonian. More generally, if you allow for, if you vary this parameter Q over P over Q, it is well known that this Hamiltonian gives rise to a so-called the stationary Schrödinger equation is the so-called Harper equation, which gives rise to the Hofstadter spectrum. So once we see this, actually we also start to see that in the Hofstadter spectrum, you can identify what let's say, the GKP states are. And let's say, so the Hamiltonian, when you consider the case P over Q equal 1/2, has a continuous spectrum from -2 to 2. So this is clearly seen by the fact that if you shift GKP states, you get still eigenstates of the stabilizers of the GKP state. And essentially, since you want degeneracy 2, eventually the GKP code can be seen as this point in the Hofstadter butterfly. Okay, but now, so this Hamiltonian is, you know, you can only get wave packets out of it because these are all unnormalizable states. But most of all, to me, the problem with this Hamiltonian is actually related to state preparation. So now we try to resort to other method to get the what they are the approximate GKP states, and the idea is actually to add a parabolic potential. So we now consider the case in which on top of the cosine potential, we have a parabolic potential. And if you repeat the previous derivation, and again you project onto the lowest Landau level, you end up with this Hamiltonian here, where here I've assumed that, again, this B0 is symmetric between the two. That is going to be important. And so what is the spectrum of this Hamiltonian and how it behaves qualitatively? So, of course, you expect that for small omega 0, what happens is that the spectrum will become more and more dense, and you will end up having, you know, everything is going to be like degenerate. So here I'm plotting the spectrum, so as a function of omega 0 divided by V, actually. And you actually see that the first two levels, they quickly become degenerate. And so when they are essentially degenerate, there is still a gap compared to the other levels. Here there is also a crossing of these levels, to say here what we should interpret as GKP state here is actually the third level. But anyway, so the thing is, we still have essentially a degenerate ground space while having a gap compared to the other states. And also this gap here, so this is the gap between the first two levels, scales exponentially with V divided by H0. So, but now the question is, what are these two levels? So are they the GKP states, or are they the approximate GKP states? And the answer is actually no, they're not, because they are the Hadamard eigenstates of the GKP code with an effective squeezing parameter that is given by this formula here. And there is a simple way of seeing that they must be the Hadamard eigenstates. So they are magic states. This is quite interesting. And the reason is that essentially this Hamiltonian commutes with the logical Hadamard gate, so the unitary that implements the Hadamard gate in the GKP code. This unitary is, for instance, this one, but the transformation that implements is the following. So it exchanges x and p, and it sends p to minus x. So in fact, so this is a let's say a theory argument for this. Indeed, if we now invert this relationship, so this is what defines the Hadamard eigenstates, you end up indeed with the ideal, the approximate GKP code words. So one thing that is quite important, so this happens, of course, when everything is symmetric. It's also true that if you now have an asymmetry, for instance, in V0, so let's say the coefficient multiplying this cosine is larger than the other one, the eigenstates end up being really the GKP code words. So in principle, you can also engineer the GKP code words to be really the eigenstates. Okay, so now the question is, can we map this mechanical problem to an electrical circuit? So of course, the answer to this question will be yes. But all current circuit QED, as we know, is based on non-reciprocal circuit elements. So which in the mechanical analogy, so they give rise to a time reverse symmetric Hamiltonian. And so since everything is time reverse symmetric, at least if we do things passively, you cannot have an analog of the magnetic field that breaks this time reverse symmetry. So we need a new element in the circuit QED toolbox, and here it's a new element in the sense that the element was already theorized maybe 70 years ago. And this element is a non-reciprocal element that is called the gyrator. So the gyrator is a two-port element theorized by Telegan, who understood that let's say this element must exist to make circuit theory complete, and indeed it was realized years later. And essentially, for our purpose, what so the gyrator is defined by this admittance matrix. Here we will consider an ideal gyrator, so everything will be perfect. So it's our dream, of course. But essentially, what the gyrator does is to introduce an analog of the magnetic field, because you can show that the Lagrangian associated with the gyrator has the following form, and you can identify an analog of the vector potential. And so this is A times a velocity in the circuit sense, where so the flux plays the role of the position. Okay, so now in order to realize the previous idea in this electrical language, we actually need something that plays the role of a mass. We need something that gives a cosine potential and something that gives a parabolic potential. So everybody that knows, let's say, circuit QED will understand that the circuit you're looking for is the following one. So with a Josephson junction, an inductance, and a capacitor. Okay, so this is a table that shows the conversion between the classical crystal electron and the variables and those of in the circuit model. The condition for having the GKP code turns out being the fact that G over G0, so G is the gyration constant, G0 is the conductance quantum, has to be equal to 1/2. So this is already a first barrier to any implementation of the circuit, because this is so far out of reach for a current gyrator, so you cannot achieve this kind of, let's say, this kind of conductance quantum. But there are ideas based on quantum Hall gyrators, and actually my collaborators are actively working on that.
So, sorry, Alessandro, you have 5 more minutes.
Yeah. So apart from that, so assuming that we have available this, here I reported some currently achievable parameters that are realized in the literature and so realized experimentally. Um, and so these are parameters that are available that are more or less, let's say, comparable to what has been achieved experimentally, and they are compatible with our approximations. So as you see, I'm here assuming a EL, that is the inductive energy, that is quite small because I would like it to be small, of course. So this means that we need, of course, superinductances. The problem is that there was that bad capacitance, that bad rescaling of parameters that eventually makes the effective ratio between the cosine and the parabolic term quite bad. And actually, eventually, with these parameters, the squeezing parameter will be 0.8, which is definitely has to be improved, for instance, by having larger superinductances. Okay, so in the paper, we also developed some ideas for doing gates and state preparation. So these are all ideas that work in the good GKP regime. So we claim that we're all mimicking the, let's say, the way we do gates in active GKP error correction. So the logical X and Z could be implemented by current sources, while the logical Hadamard and S-gate could be implemented if you have either tunable inductances or Josephson energies. That will, because it will turn on more like a parabolic term compared to the other. And actually, in a similar way, you could prepare Hadamard eigenstates and GKP logical states, but maybe I won't go too much into details. I would claim that actually having tunable inductances would be way better than tunable Josephson energies. For the reason, and the reason is that if you have tunable Josephson energies, then you always have to make sure that this lowest Landau level projection is satisfied, at least if we want really to do exactly what we discussed in this paper, in this work. So then qualitative analysis of resilience to noise. So first of all, the charge noise, so this is nice, it actually couples only to the dynamical momenta, which are not the degrees of freedom in which we are encoding quantum information. And most of all, charge noise will not be, most likely, will not be able to cause transitions between the Landau levels. So we claim that charge noise would not be a major problem, although we were working in a regime of large EC. Essentially, the noise protection will come from the fact that the wave functions have this joint support. This is quite similar to the 0 pi qubit. So this is a similar idea. And I have to say that to a first analysis, for what I've seen, and also a bit compared this 0 pi qubit Fluxonia and also my qubit here, I have to say that the way the flux noise scales with the inductance, let's say it does not seem to be inherently different from these two cases, and this actually seems to me a common feature of these kinds of qubits. And however, I also claim that, as Jonathan also said, a better understanding of the properties of the passive properties of the GKP code is needed in order to really treat this system in the good GKP regime. Anyway, conclusions. I think the nice message of the paper is that we showed this nice connection between the Hofstadter butterfly, the GKP states, and our circuit. Of course, the first barrier to its realization is the realization of a non-chip generator. However, and also GKP logic and magic states could be potentially prepared in the same way. As an outlook, so I would say that we hope that this stimulates also research in the direction of understanding better the passive properties of error correction in continuous variable systems. An interesting thing would be also to study the opposite regime of EJ smaller than EC, in which you have a tight binding model, and also that our work stimulates research in the direction of including non-reciprocal elements in the circuit QED toolbox, because I think there is interesting physics there. And thank you for your attention.
So thank you, Alessandro. So we have 2 questions by Philippe Campagna. So I'm going to ask them. Yes. So the first one is that, well, the circulators have been implemented in circuit QED, but with a limited working band in the gigahertz range. Is there a way these elements could be used to build your circuit?
I didn't understand.
So there has been already some circulators that have been implemented in the circuit QED experiments with a limited working band of in a gigahertz range. Is there a way that you can use this to build your circuit? Okay, so indeed, that is another open question. So to us, we think that eventually the important thing is that the gyrator works at the bandwidth of the of the energy levels of our system. So it shouldn't be a super large bandwidth. Then we also have some models in which we are considering to model this bandwidth by you can model them by adding capacitances, additional capacitances, either in series with the gyrator or in parallel. That actually eventually will give rise to a similar model. But again, I think that the message is that the finite bandwidth of the gyrator, of course, will play a role. It's an imperfection of the ideal model, but the bandwidth should include, let's say, in a certain sense, consistently the energy levels that you're interested in. That is the.
So, hi Alessandro, thanks for your talk and this answer. What do you mean by that the gyrator should work in the band of your energy levels? Which energy levels are you talking about? Is it the gap or is it the?
No, it's the levels that you obtain within the Landau levels.
So that's you mean that the band of the circulator should be the splitting of the degenerate eigenstates?
Yes, in those, yes. Yes, I would claim
but
that.
So that for the band, the width of the band, but at which frequency is this happening? It looks like it's happening at 0 frequency, basically.
Okay, so eventually it will be in the order of megahertz frequency, I would say. If I mean, of course, if you push it, of course, it will have to go. I mean, the better the GKP states, the better the smaller the frequency. Actually, it depends on which regime. I mean, it eventually depends also in the regime of inductance that you're considering. But let's say I would say that eventually, let's say for practical, let's say practically, I would conceive that still the splitting will be something of few megahertz. Yeah, at least in a I don't know, if you reduce the superinductance, so if you increase the superinductance by 2 orders of magnitudes compared to what I said before, which is already quite a lot, eventually the splitting will be something of 1 megahertz for the parameters I consider. So order of 10 megahertz.
So that's working from 0 to 1 megahertz or so. Actually, that ties up with another question I had: is do you really need the superinductors? Like, if you consider the circuit without the superinductors, it looks like you're stabilizing ideal GKP states.
Okay, yeah, that's a good question indeed. So as I said, to me, the point is, yeah, you're stabilizing ideal GKP states, but then if you take the thermal state, it will be a mixed state of
you know, states that are localized in, let's say, in what I call the Zach space in GKP, let's say 0 and GKP 1, but then you would have the problem that you don't actually know how to initialize the system. So you will end up with a mixture of GKP states, and then at that point, what you would have to do is to make a modular measurement in these, let's say, guiding center like variables to do initialization, which I honestly wouldn't know how to do. And in addition, also with the with these inductances, there is this nice thing that you can, in principle, engineer both Hadamard eigenstates and GKP logicals. Yeah, but I think so to me the main problem is state preparation in that case.
So yeah, but the way you propose to do it is adiabatic by adiabatically ramping down your EL, right?
Yes, exactly.
How fast is it? Like it looks like at the yeah. How fast is this? How fast can you go to prepare it? There is no divergence. Like if you go to EL.
Okay, can I go back to the yeah? Okay, I simulated this. I can tell you.
Maybe we'll have to.
Okay.
Yeah. So maybe we'll, no, we can. You can maybe answer this question and then we'll stop because.
Okay. So it is. So what I was also thinking at the beginning is that yeah, okay, this wouldn't work because you know, it's getting degenerate, and so you would have to go extremely slow. But that is not true because it might get degenerate, but there is a you know, there is this symmetry that there is a parity symmetry. So eventually, this state here has a different symmetry compared to this state here, and.
So actually, you need to be slow only at the beginning, right? You need to be slow only when they are not well defined in terms of symmetry at first.
Yeah, I mean, here, I mean, what I would claim that what matters is this gap here and not this gap here. And I simulated, I assume that I start with the state here, I go very, very fast here, the state ends up being the ground state. There is no problem with this level here. And it's because of, yeah, it's because of this, the fact that there is no connection between there is no connection between the eigenstates. And that is actually, I think that the protection in a sense can also has to do with that. Okay.
Thank you.
I agree with that. Thanks a lot.
Yeah. Thank you, Alessandro. So we'll have a break now for 10 minutes, 9 minutes perhaps. We're gonna restart at 11 Europe time. And with a talk by Ulrich Andersen. So is there